Are any of you guys taking 33A in the fall? That's the only yeah, but if I was the instructor, then you could just come to my lectures. That would be my first time being an instructor if it happens next year. Yeah. I'll think about 33A in the fall. We'll see. Again, I don't know how things are going to work out. So. You can always ask me for help in the fall, no matter what. Okay, well, while more people show up, maybe, I don't know if more people show up or not, I do have something fun to start out with to get us extremely hyped up and warmed up. And since this will be my farewell to everyone for the entire year at least. The first cool thing that I have, let me share my screen. I have a couple potentially cool things. But the first one, while we wait for people to show up, I wanted to describe calculus in 4 dimensions really quickly. So we've been doing all this stuff with the curl and the gradient and the divergence and all these fundamental theorems in 2 and 3 dimensions, and everything generalizes to higher dimensions. So just for the people that might find this interesting, I wanted to talk about what happens in 4 dimensions. And also, for the people that don't find this interesting, you can look at this, and then when you're taking your final tomorrow and Monday and Tuesday, you can think, at least I'm not doing this in 4 dimensions, because it gets a little wackier. So this is the first cool thing. This will warm us up, and then I'll start doing some math. Okay, so what do I mean by this? Oh, I guess I'll stop the poll. Unless more people show up, they can vote too. I'll keep it open. So in 3 dimensions, what does the picture look like? This is the scenario that we're pros at, right? We have these operations. The gradient, the curl, and the divergence. And I guess this can count as review just because this is stuff that you should know and you should be comfortable with. The gradient is an operation that eats a function and it spits out a vector field. The curl is something that eats a vector field and spits out another vector field. And then we have the divergence, which eats a vector field and spits out a function. Okay, so what I want to tell you really quickly in a couple minutes is what happens in R4. There's a lot of things that are the same, but there's some things that are a little different and a little weird. So in R4, we start out in the world of functions. And the gradient is the same. The first operation is the gradient. and it spits out a vector field. And it does what you think it does. So the gradient of a function in 4 dimensions would be a 4-dimensional vector. I'll use W as the 4th variable. And it would be the vector of all the partial derivatives. So it's not too surprising. The next operation, I guess I would call the curl again. These don't really have standard names at this point, but I think I would call it the curl. And do you think the curl spits out a function or a vector or what? What do you think? Damn it. Not off to a great start. Okay, so Aiden has an interesting answer. Would it be multiple vectors? Not so, it's a little weird. That was a trick question. It's not a vector. It's not a function. It's neither. In 4 dimensions, the curl eats a vector and it spits out something that we could call a bivector. And it's not really 2 vectors. It's something with 6 components. So this is a little wild. And later, if, afterwards, if anyone's actually interested in this, I can talk more about this. But let me show you what it is. So I worked this out beforehand. I'm pretty sure this is correct. There might be an issue with a sign here and there. But if you have, so what we want to do is we want to take the curl of a vector with 4 components, F1, F2, F3, F4, and you get something called a bivector, which has 6 components, and it looks like this. So there's no standard notation for this, so I'm just kind of making up names and notations. So this like double angle bracket thing, this is going to be my 20 minutes ago made up notation for a bivector. So at least you don't have to compute the curl in 4 dimensions. But then we move on. So the next operation eats a bivector and spits out a vector field. Like it spits out a genuine vector field. And this doesn't have a name, as far as I know. So I'm giving it a name and I'm going to call it the Joe operation. Books will be published about this in my honor in the future. So what is this operation? It eats a bivector and spits out a vector. So this means it eats a thing with 6 components and spits out a vector with 4 components. And I also worked this out earlier today, again, like 20 minutes ago. And up to possibly, there might be a sign error here and there somewhere, but that's pretty much it. That would be the Joe operation. So again, it eats something with 6 components and spits out something with 4 components. And then you have the divergence again. And that eats a vector and spits out a function. And it's the same, right? So the divergence of a 4-dimensional vector field would be the x derivative of f1 plus the y derivative of f2, etc. Okay, so this is a good question, and Mateen's asking the right question here, which is, if you think about this three-dimensional picture that we have, that we actually care about. Oh my God, the poll is completely tied. That's crazy. It's literally 50% for both flavors. All right, I guess I'll see what happens with anyone else that shows up to break the tie. So here's the phenomenon in 3 dimensions, and you should know this. Yeah, so this is good to know. If you go 2 steps like this, so in other words, if you start with a function, take the gradient, and then take the curl, you get 0. So in other words, this says that the curl of the gradient is always 0. Likewise, if you go 2 steps like this, you get 0. So this says that the divergence of the curl is 0. So it's not that the curl of the Joe would be 0. What we could say is that, well, so the first 2 statements, sorry, so what we would want to say is, we could say that this is 0. So the curl of the gradient is still 0. Whoops. I'll just be sloppy and I'll write it like this. Now the next thing would be this and this. That would be 0, exactly. So the Joe of the curl would be 0. And then finally, the divergence of the Joe would always be 0. And I could ask the same questions about, like, oh, if the Joe is 0, does that mean there's a vector field such that the curl of that is this bivector? Or like, oh, if the divergence is 0, can you find a bivector field such that the Joe of that is your vector field, and there would be fundamental theorems between these, and everything generalizes. So this is how things generalize to 4 dimensions. So tomorrow, when you're working on 3-dimensional math and you're stressed out and you're pulling your hair out, just take a breath and tell yourself, at least I don't have to compute the Joe. Okay, that was our warm-up. Now we can do some slightly more down-to-earth math. The poll's still tied too. Now it's still 50%. So, okay, now Blueberry's in the lead. I'll keep it going for a little while longer. Anyway, the plan for today is the same as it always is. I have a bunch of examples prepared. And I'll go until I get bored, probably around 3 hours, maybe not so much longer after that. And then we'll see. So if you ever have questions, let them rip. I guess we can start with this one, since this is the first one I had pulled up. I think this is one that I had written last night that we didn't get a chance to do. So let's see. S is an oriented surface, which is, so this is kind of hard to read. So what I'm saying is that S is the union of 2 surfaces, S1 and S2. So what is S1? S1 is the top half of the unit sphere oriented outwards, and S2 is the portion of the XY plane satisfying x squared plus y squared is less than or equal to 1, oriented downwards. we've got a vector field, and the goal of the problem is to compute the flux of the vector field through the surface. Okay. Let me draw some pictures, or a picture, or maybe some pictures. And you guys can think while I do that. So let's see, maybe I'll try to do this in red for the top half of the sphere. So they say that, or I say, I guess, I wrote the problem, that S1 is the top half of the unit sphere. So that would look like this, approximately. And it's oriented outwards. That's S1. And then what is S2? So S2 is going to be the portion of the xy plane satisfying x squared plus y squared is less than or equal to 1. Well, x squared plus y squared equals 1 in the xy plane is going to be exactly the kind of boundary of that S1 thing. So I think all this is telling me is that S2 is the base, kind of sitting underneath the hemisphere. And it's oriented downwards, so I'll draw that like that, maybe. Yes, thanks, Ricardo. So this is supposed to be union. So I just mean this and this together. Maybe I should actually write this as a plus because we're talking about oriented surfaces. So thank you for asking about that. That's probably a better way to write that. Okay, thoughts, ideas. Now it's tied again, 28 and 28. I'll say this, next vote wins. So if someone shows up and votes, I'm stopping it there. Yeah, I guess I could mix them. I did not vote in my own poll. Okay, so I think you guys are saying divergence theorem, which seems good because this is a closed surface. It encloses a region. So, you know, we could try computing the flux directly by parameterizing both surfaces and doing them individually. But this is what the divergence theorem is built for. So let me remind you of the statement of the divergence theorem. The divergence theorem says that if you have a three-dimensional region E, the triple integral of the divergence over that region, this gives you the flux through the surface. All right, it looks like Blueberry wins. That was intense. That was a good poll to end on. That was the closest, easily the closest poll I've ever had. Okay. So integrating the divergence gives you the flux through the boundary surface. And the important thing about the divergence theorem is that when we write something like boundary of E, by convention, this has outward orientation, right? So this is outwardly oriented. And it looks like that's what we have here, right? If I filled in this region, and I'll do that in my solution, I'll give it a name, I'll call it E or something, then the boundary surface, you know, both of these pieces are outwardly oriented, so the boundary is going to be S1 plus S2. And pretty much all this means is that we could just straight up apply the divergence thing. So if it were me, I'd probably say let E be the region enclosed by S. Maybe I'll color that in. Then I'll write down the remark that I just made, which is that the boundary of E is S because S is outwardly oriented. So I got a private question, which was how did we know to use the divergence theorem? You know, and I'll say again, we don't have to. If you want, you could try computing it directly, and you might be able to. But so the goal of the problem is to compute the flux through a closed surface. And the divergence theorem, what you want to think when you think of the divergence theorem is that it's a statement about the flux through a closed surface. So anytime you care about the flux through a closed surface, that's a pretty ripe situation for the divergence theorem. And so if S were inwardly oriented, how would this change things? So maybe I'll talk about that in a second with the next thing that I write down. So the next thing I would write is I would say, by the divergence theorem, the flux that we care about, which, you know, maybe in case this helps clear anything up, anytime you see flux of F through S, that straight up means the surface integral of F through S. So that's what we ultimately care about. Also, I realized watching the recording last night that you guys can see my mouse. I never realized that. So it was like very annoying just seeing the mouse in the middle of the screen. No one's ever yelled at me for that. So maybe if I like move it over here, you can't see it anymore. I just remembered that. Sorry. So the next thing I would write is I would say the surface integral of F over S that we care about, well, by my remark here, S is the boundary of E. Whoops. And if S were inwardly oriented, to answer the question, what am I writing? If S were inwardly oriented, the only thing that would change is that instead of writing boundary of E here, I would write negative boundary of E, and then I would have a negative sign to pull out. So if it were inwardly oriented, in effect, you would just have to introduce a negative sign to account for that different orientation. And then I can apply the divergence theorem. This is going to be the triple integral over E of the divergence of F. And now we just have a triple integral to evaluate. Right, so like we've talked about before, the divergence theorem, you can think about this as being a bridge from the world of surface integrals to the world of triple integrals. Now that we've walked across that bridge, we're firmly back in week 2 or whatever, week 3, and we just need to do whatever we need to do to evaluate the triple integral. So the first thing I'll do is write down what the divergence is. Let's see, so the x derivative here would be sine of xz times z. Right? So, and then plus the y derivative of the second component is 1, and then plus 2z. Okay. So that's the triple integral that we have to evaluate. What do you think? What's my next move? So we don't need to parameterize anything. Spherical coordinates could be a good idea. Does anyone see anything slick? So it is Z simple, so we could do it that way too. Okay, symmetry. So what do you mean by that? This is the next thing that I would do. Okay, so that's what I was looking for. The whole integrand isn't odd in X, but this part is. So the first thing I would do, just to make this easier, is split this up into two integrals. Maybe even three integrals, right? Let me do that. The reason I'm doing this is because in this first one, what Ricardo's pointed out is that this integrand, this is odd in X. It's like sine of X, right? So this is odd in X. And the region E, this is symmetric about X equals 0. So X equals 0 is the YZ plane, and if you chop the region with the YZ plane, it looks the same on both sides. So we have symmetry of both the region and odd symmetry of the integrand. So that tells me without any computation that this is going to be 0. So symmetric about X equals 0. So this first integral is 0. Okay, so let me make sure that makes sense to people. And this is good because if we had to actually integrate this, it seems like it would be kind of hard. Maybe not. I'm not sure. But the bounds make me feel a little uneasy. Anyway, that first one's 0. We don't have to do a whole lot of work there. Now the second one, what does this give me? This just gives me the volume of E, right? And I don't feel like doing calculus to find the volume of half of a ball. I know what the volume of a ball is. You know, this will be, so 0 goes away. So 4/3 pi r cubed, and then times a half. So I got a private question, which was, how do I know this integrand is odd? Let me do that explicitly. So if I plug in negative x for x, because sine is an odd function, I can pull that negative sign out front. And I get this. And this is exactly what it means to be odd in X, because what we have here is we've shown roughly that f of negative x, that's what this thing is negative f of x. That's what it means to be odd. And so now I'm thinking way back to like day 1 or whatever, where we had some problems that was like, you know, oh, this triple integral or double integral is 0 because of odd symmetry. So that's what I'm doing there. So then, like I said, the volume, I'll just write that down. We don't need to do calculus there. Now, Ricardo says 2z is odd. I agree. But the problem now is that the region, the hemisphere, is not symmetric about z equals 0. So odd symmetry doesn't actually tell us anything here, and we will have to just actually evaluate the integral. The conclusion that we got of 0 here, this relies on odd symmetry of the integrand together with like a symmetric region. And so for this third integral, we do not have a symmetric region. So here we could do what someone suggested earlier, which is just turn this into spherical coordinates. So 2z in spherical coordinates is 2 rho cosine phi. And then the Jacobian is rho squared sine phi. And then we could do d rho, d phi, d theta. Rho, I would probably send from 0 to 1 because the radius of this hemisphere is 1. Phi, I would go down to pi over 2, starting from 0. And theta, I'd want to send all the way from 0 to 2 pi. I think that would do it. So now we just, now we just have to do it. Let me see if I can do it quickly. There's no thetas, so I'll pick up a factor of 2 pi. When I integrate the rows, so I have this 2 here, rho cubed is going to give me a 1/3. And then sine squared over 2, I think we get a 1/2. That might be right. I tried doing that in my head, so I think that's what you get. And so we'd get 2/3. Oh, that's kind of nice. That's the same. So this is going to be 2/3 pi plus 2/3 pi is 4/3 pi. And we're done. There's like a 70% chance that that's the right answer. But once you get here, you can do that more carefully than I did. Okay. One down. We were given a closed surface. We want the flux. So what we thought is well, the divergence theorem relates the flux through a closed surface to a triple integral over the inside. So we used the divergence, turned it into a triple integral, used some clever symmetry, potentially evaluated the triple integral in spherical coordinates correctly, and finished it off. Any questions about that one? Okay, cool. Let's move on. Let me see what I want to do next. Oh yeah, let's do this one. So I think it should be pi over 2 so that the final answer is something else. So yeah, I probably screwed something up somewhere. So I don't really care enough, but I'll just say, so thank you. I'll just say, don't believe this. So I integrated rho, and that gave me the 1/3. Yeah. 2 pi came from the theta integral. The 2 here came from this. Oh, whoops. I should get a 1/4. Yeah, so thanks. And then the 1/2 came from the phi integral. So I did screw up. So this is probably not right. Okay, so you can figure out what it is if you want. I wouldn't sweat it. Which one were we going to do next? Thank you, though. Thanks for pointing. We were going to do this one. Okay, so let D be the region contained by the curves y equals x cubed, y equals x cubed plus 1, x equals 0, and x equals 1. Then we have a vector field, and calling C the boundary of this region D. And the goal is to compute the line integral of f over this curve. So as usual, I'll let you think. I'll draw some pictures. Let me do it this way. These two curves may be in red, so x cubed would look like that. X cubed plus 1 would sort of look like that. And then maybe in blue, x equals 0, x equals 1. X equals 0 is the y-axis, and then how accurate do I want to be here? I may as well be accurate. So something like that. It's a little bendy, but actually, no, that's pretty straight. That's x equals 1. Sort of. Okay, so like 90% of the problems in this class, all we have to do is evaluate some line integral. And I think someone last night pointed out that, you know, we've got like 10 million different ways to think about doing these things in general. So this is, to me, this is the interesting part of these questions is deciding what to do. That's the hard part, right? Once you decide what to do, you just do it. And we've got a lot of practice this quarter with doing stuff, so you guys are good at that. The hard part's just deciding what to do. Okay, I like the Green's theorem suggestion for a couple reasons. As always, so it seems like Green's theorem is the people's choice. I agree. Let me just write some things down. So, you know, you could think about doing it directly, as always. But this doesn't sound very fun for a couple reasons. There would be 4 different things to parameterize, right? You'd have to break this up into 4 different curves. You could do it, but who wants to do that? Not me. And also, this makes me nervous. The log of y makes me nervous. And I'm realizing I maybe should have been a little... Oh, also in my picture, I didn't finish the picture. I should identify what D is. Sorry about that. This would be D. So what would the boundary of D look like? What would C look like? Well, when we talk about the boundary orientation of a curve, I always want to walk along the curve so that the region is to my left. So let me write that down too. D is to the left. That means that the orientation here is going to look like this. It'll be counterclockwise in this case. Anyway, I don't want to do it directly because of the 4 different pieces. And then I'm a little nervous about this log of y thing, because in general, integrating logs is not very fun. And like, for example, on these cubic curves, something wild is going to happen there. But if we're thinking about Green's theorem and I'm just eyeballing the curl, I know that when I take the curl, I'm going to take an x derivative of this component, and that log of y is going to go away. So if I were to do Green's theorem, I wouldn't even have to worry about that log at all. So for a couple reasons, probably don't want to do it directly. And like you guys have pointed out, C is a closed curve. So maybe Green's theorem. Okay, so by Green's theorem, there's not a whole lot to say here beforehand, because by definition, the curve that we care about is the boundary of D. So maybe let me write it this way. The integral of f over c, is the integral over the boundary of D. That's what C is defined to be. And so what does Green's theorem tell me? Green's theorem tells me that the line integral of f around a closed curve, or around the boundary of some region, gives me the double integral over D of the curl. And now we just have a double integral to do. So let me compute the curl really quickly. The curl is going to be the x derivative of f2, which is 4xy minus 2xy. So I get 2xy. And again, I said this in the previous problem, but what we've done is Green's theorem acts as a bridge from the world of line integrals to the world of double integrals. And we've walked across that bridge. So now all we're looking at is a double integral. And we're back in time to week 2 or week 4 or something like that. We just have to do anything we need to do to figure out the double integral. So we could do a couple things, but what do you think I want us to do here? I would do a change of variables. It's been a while, so again, you don't have to, right? You could split this up into, I think, even just 2 regions. My picture is not great, but I think if you like cut this here, you could have 2 simple regions and it might not be so bad. But if it were me, and the point of this question is to practice some change of variables just since it's been a while. So goofy region. So let's do a change of variables. Oh, damn it. Yeah, you're right. I'm realizing when we're going to do a change of variables anyways, just because I want to. But you're completely right. I think what happened is I originally, yeah, this tends to happen a lot. Writing good questions is kind of hard. The first version of this question I had, instead of this line, I went like this so that it wasn't simple. And then I tried doing it, it was way too hard. So then I was like, okay, so if I change it like this, it'll be a little easier after the change of variables, but now you're correct that the region is simple without a change of variables. Let's do one anyway. And if Ricardo is to be trusted, which I think he is, he says that the integral gets kind of ugly. Yeah, probably just decent powers of polynomials. You could do it. We're going to do a change of variables anyway, because you should know how to do these things, and we want some practice. So, and again, you guys are right, it's y simple, so you wouldn't really need to. But if you wanted to do a change of variables, what would we do? What seems like a reasonable change of variables? So we could, one of the things we could do is we could say like the x direction is pretty nice already. Like it's just here and here. So maybe we don't need to do anything too intense there. Maybe I'll just let x be, gonna write it like this. What if I just let u be x? What would be a good thing to call v? Yes, I like that. If I look at these two equations, if I think about the y direction, if I popped an x cubed over to the left, I could get this equation as y minus x cubed equals 1 and y minus x cubed equals 0. So what that tells me is that a good choice for a variable change here would be to call v y minus x cubed. Okay. Now, and again, this is the kind of thing that I wanted to think about just so that you remember some of this stuff. What have we written down here? When we think about the whole change of variables nonsense, there was this problem where like sometimes we would get G right, and sometimes we get G inverse, and what we've described is a G inverse map. So X, Y, we're looking for a region U and V over here, and what this describes is G inverse. That's fine. Eventually, we might just have to figure out what G is. But first, before I do that, so maybe let me write this. What is the corresponding region going to be over here? Well, the region over here is described by x is between 0 and 1. Yeah, so it's going to end up being a square, which is why this is kind of nice. X is between 0 and 1. And then y minus x cubed is between 0 and 1. So the corresponding region over here is u between 0 and 1 and v between 0 and 1. So that gets us a square. That'll be our bounds, so that's really nice. Maybe let me call this E. So when we change to the UV world, our new bounds will just be 0 to 1 and 0 to 1. The next thing that we'll have to do is we'll have to figure out how to change this, and we'll have to compute the Jacobian of G, right? But we don't have G right now. So if it were me, what I would do is I would figure out what G is. Fortunately, it's not too hard. I think I'll need another page. If U is X, then extremely deep fact coming up. So sit down. This tells me that X is U. Shocker. So I've solved for X in terms of U and V, and I also need to solve for Y in terms of U and V. So what I could do is I could say, well, if I look at my other equation, I solve for Y, this tells me that Y is V plus X cubed. But what is X? It's U. So this is V plus U cubed. So, and I'll look at your question in a second, John. I'll finish this off. What this tells us is that, so, G as a function of U and V is X comma Y. X is U, and Y is V plus U cubed. Okay, so the question is maybe to think about this whole G inverse G thing again. And you can the naming of G and G inverse is just a convention. So honestly, you can call them whatever you want, but maybe the thing to keep in mind, and so this is what I'll write down next. So this is the abstract change of variables formula. This is what we're going to use, and this is what you should know, is that if you start with a double integral, in the XY world, and you change variables, you get the corresponding region in the UV world. And then as I've labeled things, you change the function using G, and then you multiply by the absolute value of the Jacobian of G. And there's kind of nothing you can do about that formula. Like it or not, that's how changing variables works. That was kind of the whole point of learning about the theory of changing variables. So whatever you want to call these things, like by convention throughout the course, we've been thinking about UV over here and XY over here. And we've been calling this direction G and this direction G inverse. And so when I write like the Jacobian of G here, this is the Jacobian that you need. So if you prefer thinking about it differently, that's okay. But at the end of the day, you do need this direction. You need the Jacobian of this direction. And this direction, getting X and Y in terms of U and V, that's how you're going to change the function as well. But if you want to think about it visually differently, that's fine as well. So I got a private question, which was, why do I write G with vector brackets instead of regular parentheses? I don't know. I felt like it. It's, it's a vector valued function. But if I wrote them with smooth parentheses, that'd be fine as well. You can do whatever you want. I don't even care. You could, if you're a 33A person or whatever. I would actually probably write it like this. I don't really like using these brackets notations. I have to write a comma. It takes so much time. And with this notation, I don't have to write a comma. So yeah, it doesn't really matter as long as you're clear. Anyway, we have G. So this is going to let us easily compute the Jacobian of G. And you know, we probably could have done this with the inverse, but just for practice. So the Jacobian of G is going to be the determinant of the matrix of partial derivatives, where I take x with respect to u, x with respect to v, y with respect to u, and y with respect to v. So if I do that here, the derivative of x with respect to u is going to be 1. The derivative of x with respect to v is going to be 0. The derivative of y with respect to u is going to be 3u squared. And then the derivative of y with respect to v would be 1. And this determinant is going to be 1 minus 0. So it's actually just 1. That's really nice. And so the double integral, so the Jacobian is 1. When we put it in an integral, we're going to put the absolute value of 1. But the Jacobian itself is 1. Yeah. So like if we got negative 5 million, the Jacobian would be negative 5 million. The thing that you put in the integral would be 5 million, but the Jacobian is just the determinant. So what was the double integral that we started with? 2xy over d. By our change of variables, our new bounds are going to be over e, which is the square. So what I'll write is a double integral first. And then 2xy, we need to write in terms of u and v. So x is u. So I get 2 times x times y dAuv. And then we're in the clear. So I'll finish this off really quickly. So if you integrate with respect to u and you plug in 1 and 0, you should get v plus 2/5. And so we'll get 1/2 plus 2/5, which is 5/10 plus 4/10, which is 9/10, which is what Katie got earlier. So it checks out. Nice. Okay, so even though we didn't probably have to do a change of variables, I'm guessing that this actual integration is much more pleasant than if you were to do this directly up here. Because, whoops, so like, let me just think about that. Maybe not, but if you do y first, you're gonna get like y squared And then you're going to have to plug in x cubed plus 1 and x cubed into the y squared thing. And probably things cancel out, but you'll be squaring that. You'll get like a degree 6 polynomial. So you can do it. You can definitely do it. And you don't need a change of variables here. But the point of the question was to practice change of variables, because I think it's something that you should remember how to do. Practice this like Jacobian and G inverse stuff. And then I do think the change of variables makes the actual integration much nicer. Yeah, so if you get a Jacobian which is negative, it's telling you that it's flipping the orientation, roughly. So actually, that's a good question now that we've talked about orientation. Over here on this picture, it's not really oriented, but if you pretend that this is in 3 dimensions, D is oriented upwards, right? And our Jacobian was positive, which means the region over here is also oriented upwards. But if you got a Jacobian that was negative, what that would mean is that your G function is taking you from a negatively, like a downward oriented thing, to an upward oriented thing. So the sign of the Jacobian is detecting orientation, which doesn't really matter for double integrals, which is why we put the absolute value in there. But yeah, it's a good question. Okay, so next example done. Green's theorem and change of variables, a 1-2 punch. Any questions about that one? Cool. Oh, this one's fun. Let me look at what else I have. Let's do something a little more straightforward. Then we could do something fun after that. Okay. So what we have a wire. It's defined as the boundary of the surface, x equals y squared plus z squared, where x is less than or equal to 4. And then I'm telling you that the wire has a density function, which is x plus y. And the question is, what is the mass? Ugh. What is the mass of the wire? Okay. The first thing I'll remind you of here while you brainstorm or do whatever you're doing right now is that in general, how do you get mass? You integrate density. Okay. And the reason I'm writing it in words like this rather than writing like what we'll actually care about here is because this concept extends to any kind of integral, to any kind of object. So here we have a wire. So what we're going to do is we're going to do probably a line integral of density. But if you cared about the mass of some surface, you could do the surface integral of density. Or if you cared about the mass of some 3-dimensional region, you could do a triple integral of the density. Or if we were doing our 4-dimensional calculus, and I cared about the mass of some three-dimensional hypersurface in 4 dimensions, I could do a three-dimensional hypersurface integral of the density function. So in any number of dimensions or for any kind of concept, very generally, the takeaway for something like this is that, sorry, there we are. Mass is the integral of density. So we're given a density function for the wire. The wire is presumably some kind of curve. So what we want to do in this scenario, so for us, the mass that we care about is going to be the line integral over, I guess I'll call it C, of this density function. And this is a scalar line integral, right? Maybe I'll write that down. It's been a while since we've talked about scalar line integrals. And the reason why I just want to bring this up is because, you know, we've spent all this time and energy the past few weeks talking about vector line integrals in various contexts, and we have all these like theorems and stuff. If you get a scalar line integral, is there anything fancy you can do? Not really. None of these fundamental theorems that we have relate scalar line integrals to anything. They're all about like Green's theorem, Stokes theorem, etc. These are all about, you know, the fundamental theorem of conservative vector fields. They're all about vector line integrals. So for a problem like this, or if you get something where it's like, oh, do this scalar line integral, the only thing you can do is just do it. You can't do any like sick Green's theorem maneuver or something. You just have to do it. So that's all we'll do here. We'll just practice actually evaluating one of these scalar line integrals. Okay. Preamble over. Let me draw a picture. Oh, also, so I don't know, in my preambling, I kind of, you know, said what we're going to do, but a thing to be careful about in a problem like this is, you know, you need to read math carefully. And one of the hard things is parsing the information that you're given. And we're talking about like, oh, the boundary of the surface, something. And if you trust your kind of gut reaction too much, you might read this and be like, Stokes. It's like, no, it's a scalar line integral. So the surface doesn't even really matter here. That's kind of just, yeah, it's kind of there to throw you off, to be honest. Really, its only purpose is to describe the surface. But we're not actually going to do anything with it. So this is something to be careful about, you know, when you get problems. So the surface is x equals y squared plus z squared. So that's going to be a paraboloid thingy opening in the, I guess, x direction. And then if I cut it off at 4, we would get that. So here's x, y, z. And maybe I shouldn't have drawn the surface in red, but here's C. It's this like opening of the paraboloid. Now, question, do I care about an orientation on C? Do I care about the direction that it's traveling? No, we do not. So this is a scalar line integral. Orientation doesn't matter. So I don't have to draw an arrow. It wouldn't even I mean, yeah, wouldn't really make sense to draw an arrow here. It's just a curve. Okay. So maybe let me remind you how to compute a scalar line integral. The integral over a curve of a function, ds, what do? You parameterize. And then instead of dotting with r prime, you just multiply by the magnitude of r prime, since this is a scalar quantity. And the orientation doesn't matter of r prime, so we can parameterize however we want. So that's all we have to do here. So the first question is, how could we parameterize this curve? It's, okay, I like that. So it's a circle of radius 2. I think Elijah's getting that from saying, well, the boundary is going to occur when this is an equality, right? So the boundary, so the curve satisfies x equals 4. The boundary curve lies in the plane x equals 4, which means it satisfies 4 equals y squared plus z squared. And that's a circle of radius 2 in the yz plane. Yes, so Karen's suggestion, I think, could work. X is always 4, so I'll just keep 4, keep the x component constant at 4, and then we could say y is 2 cosine t, and z is 2 sine t. And then I go all the way around the circle, so probably my domain is going to be 0 to 2 pi. That would do it. And again, do we have to check the direction or anything like that? Nope, doesn't matter. So the mass of C, like I wrote up there, this is going to be the integral of the density function over C ds, which is, I forget what the density function is, x plus y. And now I can use my parameterization to turn this into a line integral. Sorry, turn this into a regular integral. My bounds go from 0 to 2 pi. X plus y is going to be 4 plus 2 cosine t. So that's the function. Maybe I'll color code that. And then I need to multiply by r prime, which I forgot to compute. So let me do that now. So r prime of t is going to be 0, negative 2 cosine t, 2 cosine t, sine of t rather here. So its magnitude is, let's see, 2, I think. So I multiply this guy by 2. And now we're back in 31a. So let's see, I think we get 8 times 2 pi is 16 pi. And then when you integrate cosine from 0 to 2 pi, I think you'll get 0. So I'll do it. So the mass is 16 pi. So nothing fancy here. We were just given a problem, find the mass of some wire. that's the scalar line integral. Can't do anything fancy because it's a scalar line integral. So all we can do is evaluate it. Nice. Okay. Let's see. Any questions about that one before we move on? It might be snack time for me. So let me find another one to pull up and then I'll go get my yogurt, which was blueberry, right? Blueberry one. Okay. Okay, this one's fun. You can either take a 2-minute break, whoops, while I go get my food. Or if you want, you can start thinking about this next one. This will be next up. I'll be back. Okay, back in business. Whoops. Yeah, I think things froze. Okay. So we have a vector field, which looks like that. And I'm telling you that it's defined on all of R3 except for the y-axis and the z-axis. And I drew some curve in this picture. So we're going to have to rely on my artistic abilities here. And the question is, surprise, what is the integral of f along the curve? Okay. Now, I'll get us started. One thing we definitely cannot do is evaluate it directly because we don't know what the curve is. I just drew a stupid picture, right? So we have to do something clever. And also, maybe let me just make sure that my picture makes sense, because this is important. Hopefully it's clear enough in terms of like wrapping around or whatever. But if you think about this brown cross, which is indicating the y and the z axis, those are the things that like are not a part of the domain. Then the red curve kind of wraps around both in some sense. Okay, so let's take the divergence. I don't know what that would get us. Okay, so, oh, I like Katie's idea. You know, we could think about like, is it conservative? You know, because if it is, it's a closed curve, it would be 0. But the vector field should feel familiar, or it should have some pieces that kind of feel familiar. And I think this is what Katie's getting at. And yeah, it feels vortexy, right? And I do really like the idea of splitting this up into 2, because this might make things easier to deal with. So what do you think? So first, what the... What 2 vector fields? I'll just do it. I won't make you type that in the Zoom chat. Anyway, I do think it's a good idea to split this up into 2 vector fields. I think that's a great idea. So let me write F as, so one of these vector fields, I think we should do, so if I look at the denominators here, I've got like x squared plus z squared, x squared plus y squared, x squared plus y squared, x squared plus z squared. Let me collect the x and z things, and then I'll collect the y, the x and y things. So one of these vector fields could be negative z over x squared plus, z squared. 0, and then x over x squared plus z squared, plus, what do we have left? We have a y over x squared plus y squared, negative x over x squared plus y squared, and 0. So, this is starting to feel like homework number 2. let me give this a name. I'll call this G, and I'll call this H. And so what we've done now is we've decomposed F as G plus H. Why could or why would this help? It's not a bad idea just because integration is linear, right? We could split the integral up into two completely unrelated integrals. So by that I mean the integral over C that we care about of F, I could just split this up into an integral of G plus an integral of H. And these are two completely different things. They don't interact at all. I can treat them completely separately. So let's treat these separately. Okay, so let's think about G first. Here's where I might want ideas. And also we'll have to be, we could write this in a number of ways, but since my curve is just like a random picture of the curve, like I wouldn't worry too much about it. So let's do G first. Yeah, I'll post them. Afterwards, I'll post this whole document, which has stuff from both last night and today. I'll post it on my website. Yeah, although I think the office hour notes are pretty updated. Maybe not from Thursday. I'll update those too. I think Thursday was pretty quiet though, so there might not be anything too exciting there. Okay, so G is up here. If I only wanted to integrate G over the curve, what could we do? Another question I could ask is, what do you think the answer is for G? You might have to think a little hard here. I'll let you think for a second. If no one has any ideas, then I'll go for it. I'll eat my yogurt in the meantime. I don't think it'll be 0. So what do we know about G? So maybe here's a question. What is the largest possible domain for G? Yes, everything but when x and z are both 0, which is the y-axis. So is everything except the y-axis. So that means in this picture, where we only care about g, I don't have to remove the z-axis, right? The only thing I have to remove is the y-axis. Okay. What other things might be interesting to know about G? Why would it be simply, so I agree, but why would it be conservative? Okay, good. So I bet the curl is 0. And we know that already, right? Like if this is literally the vortex vector field in the XZ plane. So we've done this computation a lot. The curl's going to be 0 here. Maybe I won't do that for now. If you don't believe me, you can check. But the curl of G is 0. So, for example, like Ricardo says, that means that this is conservative in simply connected domains. But the problem, right, is that does C live in a simply connected domain for G? The answer is no. The point of C is that it like wraps around the y-axis, right? So you can't contract that curve. Okay. You all know how to do this. It's not that hard. You got to trust yourself, trust your training. Let me draw a projection into the XZ plane. We could do curve arithmetic, but I'll ask you again. So if I looked in the XZ plane, that would be like standing over here and looking this way. What would we see? You know, I don't know exactly what the curve looks like, but it would look like this. So I'll ask again, what should this integral be? I don't need an argument for why, or I don't need a precise answer. I just want the value of the integral. I agree it'll be non-zero, but what number will, yeah, it'll be 2 pi. It's going to be 2 pi. This is what we want to show. The vortex, we've seen this a lot now, the vortex vector field measures change in angle. And this is some loop that goes all the way around, so it's going to be 2 pi. What we have to do is we just have to make a semi-formal argument for that. And like Ricardo pointed out, we could do something like curve arithmetic. We could draw, maybe in purple, I could say let D be the unit circle or something in the XZ plane oriented counterclockwise in the XZ plane. So maybe that would look like this. Whoops. I bet we could figure out what the integral over D is. I'll do that in purple. Then D is parameterized by R of T is, so it's a unit circle in the XZ plane oriented counterclockwise. So this could be like cosine t, 0 sine t for t between 0 and 2 pi. And now we can just compute, right? We know what g is. So then the integral over, over d of g is the integral from 0 to 2 pi. The vector field here, x squared plus z squared is 1 because we're on a circle. So I'll get negative z 0 x, negative z 0 x. So that'll be negative z 0 x dot r prime is negative sine t 0 cosine t dt. You get 1. So we've done this computation like 10 times this quarter. You get 2 pi. Okay. So the integral over d is 2 pi. That's not quite what we want. We want the integral over c, but we could do a couple things to show that this integral is gonna, oh, and I'll try to draw. What we want to do is we want to show that the integral over c is the same as the integral over d. And this is where we could, for example, do some curve arithmetic. We know that the curl is 0. You could also use Stokes Theorem. This is what I did last night. This is what I suggested at the end of class on Friday. So that's probably what I would do. But since I did Stokes Theorem last night, let me do some curve arithmetic just for something different. So what would we do? We could draw in a couple lines, maybe L and K. And then give things names. Maybe this is D plus, D minus, C plus, C minus. And the idea here is that, for example, this loop is going to be contained in a simply connected domain. And I could identify that simply connected domain. God, Stokes Theorem is so much easier. I would definitely just do Stokes Theorem. Even if you have to describe a weird surface, as long as you can describe it clearly enough. Then we don't have to give names. This is what I was ranting about last night, that you don't ever have to do curve arithmetic ever again if you don't want to. But we'll do it anyway, just because I think Noah seems to like it, and Noah said that, you know, something like this would be on the exam. Okay, so what am I calling this region? Smiley face. And now that's on the two-dimensional picture, but it should kind of be clear what I mean by that in the three-dimensional picture. So, and you can make things more explicit, but I could say, let smiley face be the region in blue in the two-dimensional picture. That's not quite what I mean. Let smiley face be the region in blue. Let me just say the region in blue. Which represents a three-dimensional domain. The point is that smiley face is simply connected. So what do we know about the integral of g over k plus d plus L minus C plus, that's this loop, it's going to be 0. Yeah, so this is similar to the cylinder one that I did yesterday. So if it were actually me, and we could do this if you want, we could do this for the next part, but I would just say that there's a surface, I would say there's a surface connecting these guys, and I would orient it. Then I'd say by Stokes theorem, the curl's 0, so this equals this. Done. 10 million times easier than doing curve arithmetic. But for the sake of variety, we'll do some curve arithmetic. Anyway, so the integral over that closed loop is 0. So similarly, blah, 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 blah. The integral over the bottom loop, so like k minus d minus plus L plus C minus, k minus d minus plus L plus C minus of G is 0. Then we can add them together or something like that, and that'll give us probably give us the integral over C of G. So let's see, what would I want to do? I would probably want to take this one minus this one. So if I take this minus this, we get 0 because it's 0 minus 0. And then what is the left-hand side? K minus K goes away. L minus L goes away. We'll get the integral over negative D minus minus D plus. That's negative D. And then here we have C minus negative C plus, C minus minus negative C plus, which is C. So the integral over C equals the integral over D, and we show that that's 2 pi. Oh, okay, so after some curve arithmetic, we have shown that the integral over G, the integral of G over C is 2 pi, which hopefully is intuitively clear. I think it is for some of you guys because you told me that a long time ago. And if you want to do curve arithmetic to show that, this is the kind of thing I would do. How's that so far? We're not done because that was half the vector field. The other half's going to be the same, right? Roughly. We'll just have to be a little careful about orientation. But that's the integral of G over C. That's one way to do this. Maybe I'll do the integral of H over C my way, so that you can see the two different kind of equivalent arguments that I'm talking about. So far, so good. Or you're not listening to me, which is, I don't blame you. That's fine too. I'm having fun, so I'll finish this off. So now we care about the integral of H over C. Oh yeah, thanks. Thank you, Elijah. So the integral of H over C, I could copy this picture again. Sorry, I'm scrolling a lot. One more copy paste. The largest possible domain for H would be R3 minus the z-axis, right? The only point where this isn't defined is the z-axis. So that means I don't have to remove the y-axis. I just need to remove the z-axis. Okay. So I'll project this picture again. I'll draw a two-dimensional version. There's nothing interesting happening in the z direction, so all I really care about is what's happening in the x and y direction. And if I project the picture, what would I see? Well, I'd have this hole at the origin that represents the z-axis. And then what would the curve look like? This is going to look counterclockwise again, right? So pretend that you're flying up here and looking down that way. It would look counterclockwise. So I'll ask you again, but be careful now. What is the integral of h over c? Yes, it's going to be negative 2 pi. Why? This is the negative of the vortex vector field. The usual vortex vector field is negative y over blah, 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 and x over blah, blah, blah. This is y and negative x. So this is like a vortex field spinning clockwise. So because this curve is going counterclockwise, this integral is going to give us negative 2 pi. So actually the answer at the end of the day will be 0. So I think maybe Elijah was correct. But it's 0 for a very non-trivial reason. Let's see. So how would I do this? I would say what letter do I want to use? E. Let me let E be the unit circle oriented counterclockwise in the XY plane. Okay. By almost an identical computation, we could, whoops, need an arrow here. You could compute that the integral of h over e is negative 2 pi. Just for the sake of moving on, I won't include that computation, but it would be exactly the same as what I did up here in purple. You just parameterize the circle, you know how to do that, and it's going to give you negative 2 pi because of this extra negative sign. And what would I say, instead of doing all this annoying curve arithmetic stuff, if it were me, I would say, let S be the annular surface whose boundary is C and E. So what do I mean by that? There's some surface, which is a little hard for me to draw in the three-dimensional picture, but you can think about like a weird ring, like a weird annulus that kind of connects these two curves. On the two-dimensional picture, that would look like this. So like the projection of the actual picture would look something like this. So this is what I'm calling S, and I'll orient it upwards. So here's a normal vector. I'm oriented upwards. So question for anyone who's still with me, if there is anyone, what does that tell me about the boundary of S? Yes, it's going to be C minus E. If you, for example, in this two-dimensional picture, upwards is going to mean out of the computer screen, so pointing out at you. And if you think about curling, the curling motion would go like this and like this. This matches the movement of C. And this disagrees with the movement of E. So the boundary of S will be plus C minus E. And then I got a private question about why is this 2 pi? Maybe let me do that really quick. Let me write down the boundary here. So this is going to be C minus E. So let me do this in blue. I could parameterize this curve by cosine t, sine t, 0. And I got a private question, which was just, I just decided to make it upwards. That's correct, for no good reason. You could make it downwards if you wanted to. You just need to give it some orientation. Either would work. 0 to 2 pi. And so what does this integral turn into? This is going to be 0 to 2 pi. What is the vector field here? The denominator is 1, because we're on a circle. Y is sine of t. Negative x is negative cosine t, 0. And then dot r prime is negative sine cosine 0 dt. So you get negative sine squared minus cosine squared, which is negative 1. So you get negative 2 pi. So that was a little fast, but that was the computation there. The intuition is that it's negative 2 pi because this vector field is the negative of the vortex vector field. So normally the vortex vector field looks like this, but our vector field is pointing the opposite way because there's a negative sign. So this kind of looks like that. Okay, so what does Stokes theorem say? The surface integral over S of the curl of H, rather. This is the integral over the boundary of S of H. But the curl is 0, right? The curl of this vector field is 0. So this whole surface integral is 0. But the boundary of S is C minus E. So the integral over C minus the integral over E equals 0. So they're the same. And we showed that the integral over E is negative 2 pi. That's the alternative argument to curve arithmetic. And in my opinion, this is like 30 times better at least. So it's this, this compared with this curve arithmetic stuff where you give things names and you have to do that kind of thing. That's what I was talking about. Anyway, so the integral of h is negative 2 pi, the integral of g is 2 pi, so the integral of f, to finish this off finally, is 2 pi plus negative 2 pi, which is 0. Done. So I was a little fast by the end. Sorry if I went through some things too quickly. And you might not believe me when I say this, but this problem, I don't think it's as hard as it maybe seems. It's either just a curve arithmetic, it's like 2 curve arithmetic problems in one, pretty much, or 2 Stokes theorem problems in one. You just kind of have to recognize that given a situation like this, it's probably advantageous to split this up into 2 vector fields, and then you have 2 simpler problems that are kind of completely unrelated to deal with. That was kind of the spirit of that homework question from homework 2. Same kind of deal here. Okay, so I had fun with that. I don't know about you guys. That was probably the most intense question I had for today. I doubt you'll get anything this hard on the exam. But I'll repeat that if you think about Noah's example from Friday, he did some curve arithmetic stuff with curves in 3 dimensions. That's all I'm doing here. I'm doing exactly the same thing that he did. And he said that there would be something like that on the final. So something with curve arithmetic in 3 dimensions or Stokes theorem type stuff. Maybe something like that. I think the Stokes theorem is way better, in my opinion. And for practice final number 1, question 3D, same deal. Noah's posted solution, I think, implies some curve arithmetic stuff. I would do pretty much what I did here. So really, this question is very similar to 3D on the practice final. They're pretty much the same question. They're almost identical, actually. Yeah, I definitely prefer the Stokes theorem argument. I think it's much cleaner, which is why I was ranting last night about how you never have to do curve arithmetic ever again if you don't want to. Or you never have to do surface arithmetic ever again if you don't want to, because because the divergence theorem just subsumes that. No, I mean, I don't think, if you do, based on, so when I brought up like, oh, you could do Stokes theorem at the end of class on Friday, he was like, yeah, you could do that, but that, you'd have to describe a weird surface. So I think it depends. If he writes a question like this, he's probably looking, or his answer is probably curve arithmetic. Mine would probably be Stokes theorem. Either's fine, as long as you do correct stuff, you can do whatever you want. So if you execute any method perfectly, then you're in business. Okay, let's do something easier. I think we need a comparative break after that one. Unless there were other questions about this one before I move on. Again, I think it seems intense, or it seems difficult, but this is sort of a long conglomeration of some techniques that I know all of you guys can do. Even if you don't believe in yourself, I believe in you. So can I explain why I excluded certain axes in the separate parts? Yeah, okay, that's a good question. So Yeah, that's a great question. I should have explained that more. For example, in my Stokes Theorem thing, let's think about this. Thank you for bringing that up. If I had not excluded the y-axis, so if I said that the domain still didn't include the y-axis, it might be kind of hard to see in my picture, but this surface, this like annulus thing that I defined, it runs into the y-axis, right? So the real reason that I excluded the y-axis in this part of the solution was so that I could define this surface. Otherwise, I wouldn't have been able to define my green surface, if that makes sense. And then, well, what about my curve arithmetic stuff? If I did not exclude the z-axis, this blue domain that represents like a blue thing up here, it would not be simply connected. So I would not be allowed to say this. So in the two different kind of versions of what you could do, you do have to exclude the axes. In this case, it was to ensure that this blue domain that I colored in to do curve arithmetic in is actually simply connected. If I don't exclude the z-axis, it's not simply connected. And here, if I don't exclude the y-axis, I can't define this green annulus type thing because it would run into the y-axis. That's a good question. Thank you. Oh, okay. Let's do this one. Here's a vector field. Is it conservative? And if so, find a potential function. Thoughts? Feelings? So we could find the curl. So really quickly, I got a private question about, didn't I exclude the z-axis for the green thing? Oh, okay. So this is confusing. Hopefully this wasn't too confusing. I was abusing the word excluded. So when I said, that's a good point. So I don't know if this makes sense now, but when I said I excluded that's confusing. When I said I excluded the y-axis here, I guess I meant I was excluding it from my exclusion. So here I was including the y-axis, you're correct, and here I was including the z-axis. And I guess when I was thinking about like, oh, like that's confusing. When I took out the y-axis, I meant like I took it out from the things that I was taking out. Yeah, that's a good point. I don't know if that clears it up. Okay, so is the potential function y arctangent of x plus z squared? Let's check. So let me just declare f of x, y, z to be y arctangent of x plus z squared. Then the gradient of f is, well, the x derivative is going to be y over 1 plus x squared. The y derivative is going to be arctangent of x. And the z derivative is going to be 2z. And look at that, that's f. So what have we shown? first of all, we've shown that, you know, f is defined everywhere. So since f is defined on R3, f is a potential function for capital F. Therefore, we found the potential function. And this shows that capital F is conservative. Done. That would be my solution. Now we can talk about it more if you want. So like if any of you are wondering like, where did this thing come from? We can talk about that too. But like if I was reading a test and if this was on the test and I read this solution, this is a 10 out of 10. In my grading scheme, in my book at least. The point being, so, you know, Ricardo mentioned earlier that we could take the curl or something like that, and you could definitely do that. You could totally do that, but at the end of the day, if you can find a potential function, that's what it means to be conservative. And so, yeah, so this is kind of what I was saying is that, in my opinion, if you just eyeball this function, which is presumably what Katie did, I think, or maybe she did some harder work, but I don't think it's too hard to just look at this and like do some quick partial integration in your head and just kind of eyeball that like, yeah, this should probably work. I don't think you have to justify like where you got that from. If you demonstrate that it works, that's all that matters, right? So I don't think so. But yeah, if you want to, like if you definitely could be more explicit about the partial integration, like you could say, yeah, and if you can't eyeball it, then you could just say, well, if there were a potential function, I know that it would have to be the x integral of the x derivative. So what would that look like? Well, y is constant. Antiderivative of 1 over 1 plus x squared is arctangent. So I know that this would have to look like y arctangent of x plus possibly some function of y and z. And then you could go from there. So you could absolutely do the partial integration explicitly if you want. That's totally awesome. But, you know, if 72 hours isn't enough time and you're running short on time, then, you know, you don't need to. You don't need to do anything. You're an adult. You could just skip the problem if you want. But, you know, like I said, just for an example, to me, this would be what I have written right here. That would be a fine solution. Yep. I mean, I've said that before too, right? And I've said it in a joking manner, but and you know, Noah kind of said this in a joking manner, but this was truly and honestly the intention of the sappy advice that I gave in discussion this week, which is like, you know, maybe not with this test, but in the future or whatever, if you have a hard homework assignment or if you have a really hard test question or something and you just can't figure it out and it's really stressing you out and it's giving you a lot of anxiety, just don't do it. It's just a grade. And I know it doesn't feel like it, but a bad grade is not going to impact you in any reasonable way in the grand scheme of things. So yeah, I mean, if you get a question and you know, you're like, oh, I don't know if I should do it, just don't do it. You'll be fine, move on. Okay, so private question, just to confirm, in the general case, if the function Right, so if the function you eyeball isn't defined everywhere, that f is defined, that would not be a potential function on that domain. That's correct. So here, because because the question was, is this vector field conservative on R3? What we're looking for here is a potential function that's defined on R3. So if you were only able to find a potential function defined on, like, you know, half of R3 or something, that would be a potential function for half of R3, but it would not be a potential function on all of R3. That's correct. Any other questions about that one? I'm just looking at all the other stuff that I had prepared. I'm pretty content already though with like what we've covered. Let's do that one. Let me just check. Okay. Let's do this one next. Yeah, then we can do the one with 3 circles after that. Starting to feel it a little bit. I don't know what I was on that first midterm review session. I don't know how I made it that long. Lightning struck. I'll have to strike again someday. Okay, so we have a conical surface. No caffeine that night either. I haven't had caffeine in a long time. It's been almost 3 months to the day, actually, believe it or not, since I've had any caffeine. Anyway, we have a conical surface, z equals 2 minus the square root of x squared plus y squared. Z is bigger than or equal to 0, oriented outwards. Okay. And we have a vector field, and we want to compute the flux of the vector field through the surface. Let me draw a picture, and you guys can brainstorm. So let's see, z equals 2 minus blah, 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 blah. This is going to be a cone kind of opening down like that. Something like that, at least. There's S. And it's oriented outwards, which maybe upwards would have been better, but that probably means this. Okay, so, you know, the next thing I'm going to ask is ideas. And I'll give you one idea again, which is we could try to do it directly. And maybe you could do it. It doesn't sound very fun to me just because, for example, this Sometimes it could be directly though, so you always got to think about it. But here I don't really like that, mostly because of this. Like if I raise z to the 10th, that sounds horrible. Okay, and so we have a couple ideas, which are Stokes Theorem or the Divergence Theorem. And I will say yes. Now, I'll look for something a little more specific. So let's think about Stokes Theorem. If we use something like Stokes Theorem, what would you want to do? Maybe let me just write down. Okay, so who's got an objection to that? In theory, we could, but what would we have to integrate? So not quite. So that would be going the wrong direction. Exactly. So this is why I'm a little hesitant here. If you want to use Stokes' theorem directly, Stokes' theorem concerns the surface integral of the curl of something. So what that means is that you would have to find a vector potential for f. And I think I said this in discussion, but you will never be asked to find, maybe, probably, you'll almost certainly not be asked to find a vector potential ever. So if you ever get to the point where you're doing a problem and you're like, okay, now I need to find the vector potential, that's a red flag. And that means that probably you want to be doing something else, because finding a vector potential in general is very difficult. Okay, and so we have some other ideas, which is exactly correct. We could certainly do this. We could do the divergence theorem. So I think Katie suggested that too. And maybe Kimberly did earlier as well, or someone. Yeah, and so I think there's some good ideas here, and there's a couple things we could do, but what we want to do either is, let me draw in a new surface here. And so the suggestion is Seth saying the disk, so I'm assuming that means this. So let me call that T. So maybe I'll specify this. So let T be the disk. So what would that disk be? It would be when Z is 0. So it would be the disk x squared plus y squared is less than or equal to 4 in the xy plane. Now we're talking about flux and stuff, so we need to orient this thing. So oriented okay, Mateen says downwards. But again, so I've said this before, but you know, pretty much anything would work. You just have to make a decision and be consistent with it. So if you felt like orienting the disk upwards, that's fine. Yeah, that's fine. So Let's orient it downwards though. Why not? Then, if I want to use, for example, the divergence theorem, I could fill in the cone. I'll call that E. So let E be the region enclosed by the cone and the disk. Then, since we decided to orient T downwards, so maybe I'll say, since S plus T is oriented outwards, the boundary of E is S plus T. Okay, so what would the divergence theorem say? And I actually, so this is probably what I would do, but I want to give you another solution too, and it's going to differ starting here. But I'll come back to that, and maybe I'll ask you guys for a slightly different solution, which is really secretly the same solution, but slightly different. So if you already see the end of the road, you can start thinking about a slightly different way to argue this. But by the divergence theorem would say that the triple integral over E of the divergence of F is the surface integral of F over the boundary of E. Well, the boundary of E is S plus T, so this is going to be the surface integral of F over S plus the surface integral over T. So I got a private question was, could I explain again why using Stokes theorem directly maybe wouldn't be so great? So let me write down Stokes theorem again. To be, I'll use G here. Whoops. So the reason why a direct application of Stokes theorem wouldn't be so good, because if you look at the thing that we're trying to compute, it's the surface integral of F, and then you look at the surface integral in Stokes theorem, it's not the surface integral of like a vector field, it's the surface integral of the curl of a vector field. So in order to use Stokes theorem, what you would have to do is you would have to figure out how to write F as the curl of something. In other words, you would have to find, because we have G here, so in order to use Stokes theorem directly, you would have to find a vector potential G for F. And finding something whose curl is this thing is probably really hard. Okay, and then I got a private answer to my question, which was, alternatively, we could do surface independence. So yeah, I'll come back and talk to that. So S plus T is oriented outwards, kind of, oh, that was a private question. Why is S plus T oriented outwards? It's sort of by definition of T. Like we just decided to orient T so that it's pointing down. So like T is pointing out of the region, and then we were told that S is pointing this way. So roughly because of our decision to orient T downwards, the surface is oriented outwards. But again, it doesn't have to be, and if you oriented things differently, that's totally fine. You just have to be consistent. So yeah, exactly. The kind of alternative argument would be surface independence, so I'll come back to that. Anyway, let's compute the divergence of F. I forget what the vector field is, so. So the divergence is going to be negative 2x plus 0 plus 2x. Ooh, and that's 0. Oh, wow, so this is really nice, right? The divergence is 0, which means this whole triple integral on the left is 0. So the divergence theorem tells us that this plus this is 0. So the surface integral of f over s, which is ultimately the thing that we care about, this is negative the surface integral over t. And I think, as Seth pointed out earlier, the point here is that doing the surface integral over t is probably going to be a whole lot easier, because on this disk, z is 0. So like this is 0, this is 0, this is 1. So it'll probably be a lot easier. And now we just have, actually, let me, before I do that, let me give you the alternative argument as well. So that's one thing we could say between the green lines. But alternatively, we could do a surface independence argument. So we computed, I'll just sketch this out maybe. The divergence is 0. We just showed that. And f is defined on R3. So if you think back to like Monday or something, what does that mean? That tells us that f has a vector potential. We just don't know what it is, but it does have a vector potential. Oh my God, that's terrible. Sorry, that says potential. So we can use surface independence. And in particular, we could, using surface independence, we could pick this new surface and, you know, up to orientation, say that integrating over this is going to be the same as integrating over this. Since we decided to orient t downwards, the boundary orientations will not agree, which is why we get a negative sign here. Like this, the red boundary would go this way, and the blue boundary is going to go the opposite way. So by surface independence, that's where the negative sign comes from. But anyway, that's kind of the alternative form. You could either think about this as being a consequence of the divergence theorem, or pretty much equivalently of surface independence. Anyway, however you want to make this conclusion, the integral over s is negative the integral over t. So what do we want to do? We want to parameterize t. How could we do that? Sorry for zooming in and out a whole lot. Yes, so t is the unit disk in the xy plane. That's correct. Oh yeah, you're right. It's not the unit disk, it's the disk of radius 2. Thanks. Yep, so it'll be, oh, well, I don't know about that. I think you're thinking of something correct. Sure, something like that could work, yeah. There's a couple things we could do, but we could say G of, so the first, I guess, Ricardo was first, so I'll use his letters. R cosine T. This could be R cosine T. Maybe I'll compromise. Let's use R and B. How about that? Keep things interesting. I don't think I've ever used B as a parameter before. It makes me a little uncomfortable. That's okay. Oh, and I forgot my 2. So then 2 are, oh wait, actually, oh, sorry. So they're slightly different answers, right? And the difference is the domain. So Ricardo said R cosine T. Mateen said 2R cosine T. Which one's correct? They could both be correct. It's what's important is your domain. So let me do 2R cosine of B and 2R sine of B and then 0. And with this choice, we would send B from 0 to 2 pi. And R, since we picked the 2, or since I decided to write a 2 there, R would send from, I would send from 0 to 1. But if you do what Ricardo wrote in the chat exactly, where it was just like R cosine of B, that's totally fine, but you would want to send R from 0 to 2 to account for the radius there. So again, you know, I've said this 9,000 times this quarter. Many different ways to parameterize the same thing, and as long as you do something correct, you'll be fine. Anyway, there's a parameterization. So let's compute the normal vector to check that the orientation is correct. So since I picked R and then B, I have to take the R derivative cross the B derivative. I'll give myself a new page too. Let's see, so the R derivative is going to be 2 cosine B, 2 sine B, 0. The B derivative is going to be negative 2R sine of B and 2R cosine of B, and 0. And if we cross these, we'll get 0, 0, and then 4R, I think. Question, is this oriented correctly? No, it's not. The vector 0, 0, 4R points up, and we decided to point the normal vector to T down. So that means I've got to change the orders of my parameters. So I'll do this in post. Rather than copying down, I'll just like switch them. B and R. This would give me I would cross these in the other order. Duh. Okay, I brought that along for the ride. And I would get negative 4R. Okay, now it's oriented correctly. Good stuff. And now we can compute the surface integral. So the integral over S is negative the integral over T, which is going to be negative. Our parameter bounds are, so B goes from 0 to 2 pi. R goes from 0 to 1. What is the vector field? So Z is 0, right, in our parameterization. So I'm going to get negative x squared. So I'll get negative 4r squared cosine squared b. Cosine of z is cosine of 0, which is 1. Z is 0, so that first term is 0, and then then x times y is going to be 4r squared cosine of b sine of b dot the normal vector dr db and then we're in the home stretch. It looks like we get negative 16. 4 squared is 16, right? Yeah. R cubed. My 16 kind of looks like a b, which is very unfortunate in this problem. Cosine of b sine of b. Negative signs cancel out. We'll get a factor of, so r to the 4th over 4. So I'll get a factor of 1/4. And then when I integrate the b stuff, I should get sine squared over 2. Oh, I guess we get 0, right? I think you get 0 in the end. Since we're integrating from 0 to 2 pi. Nice. All that work to get 0 again. When in doubt, the answer is probably 0. Okay, so private question is, for surface independence, could you parameterize the xy plane, specify bounds in polar coordinates, and solve the double integral over t instead of s? I think that's what we just did, right? I would describe that as pretty much what we just did. Is instead of integrating over s, we decided to integrate over t. And then we cooked up a parameterization, which was kind of motivated by polar coordinates. But, you know, it's just a parameterization at the end of the day. And then we solved the double integral. So I would say yes. But to me, that's kind of what we just did. Yeah, there seems to be a trend of doing a lot of work to get 0. That's symmetry coming into gear. Lots of good problems in math have symmetry. So comes with the cards. You're welcome, David. Have a good one. Any other questions about that one? So the big picture here, I think we did quite a bit here. The summary is we had a surface and a vector field, and I want the flux through the vector field. We ultimately picked a different surface, either by the divergence theorem or by a surface independence argument, and instead computed the flux through the simpler surface. That's the takeaway of this one. Okay. Let me do, I think maybe, I forget who. Someone had asked about this one. Oh, let me check what I've left. The last two are insanely boring, so this might be the last interesting one. That'd be perfect. Okay, here's the plan. Let me do this one, and then we can officially call it a year after that one. So I got a private question, which is, could I possibly say an example of a simpler surface for this surface independence method? So maybe, I don't know if this was clear, but let me go back to that example. Both methods use the same surface. So I'm using T in both of them. Maybe that wasn't clear. The ultimate conclusion here, like the point is to get this. So the two methods, maybe I'll say like in orange, you could either do this or you could do this. And both of those things will lead you here. Yeah, and so for both of those, I defined T up front. That was like the first thing I do no matter what. And so for both methods, I'm using that disk as the simpler surface. Yeah. What was I saying? Yeah, let me do this one. I'm starting to get pretty tired. And I've said pretty much everything that I want to say in terms of math content. So we'll do this one, then we can call it quits, and I can hang around for a little bit to answer questions or something if you guys have them. I don't think this one will be too bad. Let's see, so we have a vector field on R2 minus P and Q. I'm telling us that the curl is 0. I'm telling us that the integral over A is -2, the integral over B is 4. And the question is, what is the integral over C? So let's see, will it be 2? It'll probably be, yeah, it's probably going to be 2. I think that's right. So what we've got to do is figure out how to do this. And again, this will maybe, let me do something slightly different, which is you could do this using curve arithmetic. You could draw some lines connecting things and identify a bunch of loops and use simply connected domains. That would totally work. But like Elijah points out, we could use Green's theorem. And I think this is going to be easier. Now, we might have to be a little careful. So here's one thing we could do. Let's see. What would I do? I would chop the blue thing up into 2 different curves. So let me call B plus the part to the right of the green thing, and then B minus the thing to the left of the green stuff. And then I'll chop C up into a couple pieces too. So C plus can be this chunk here between the blue things. And then C minus will be this stuff out here. And here's what I'm going to do. So I guess I could ask for ideas and stuff, but I'll just tell you what I'm going to do because I'm tired. I'm going to identify two regions. One of them is this. Let me call that D. Kind of looks like a P. And then the other region, maybe in blue, is going to be this. Okay. I'll call that, I don't know, what do you want to call it? Let's call it Q. Why not? You're with me so far? First question for you guys is, what is the boundary of D? So we have to be a little careful here, and this is why I gave, oh, and sorry, I know it's confusing. Maybe I'll ask again. Keeping in mind that I like named these things different things. I think you're maybe thinking of the right thing. And so yeah, I got a private answer, which was C minus, or C, but C minus. So part of the boundary of D is this guy. And that would be C minus minus B minus. And yeah, and then we have this component, and this is going in the wrong direction, so it would be negative A. So think about that for a sec. So the boundary of D, I would say, is C minus minus B minus minus A. Because when we talk about the boundary orientation for a curve like A, I want D to be to my left, which means I need to be walking this way. Okay. What about the boundary of Q? Note is, what does that mean? Yeah, that's a sign that I'm starting to lose it. It's been a long quarter. So the boundary of Q, this one's a little easier. This is going to be B plus minus C plus. How's that so far? Is everyone on board with that? I defined these funny regions somehow, and identified their boundaries. The reason why I did that is because I'm going to use Green's theorem. So by Green's theorem, the integral over D of f, sorry, the double integral over d of the curl of f, which is 0, by the way, so that's going to be pretty easy to figure out, is the integral over the boundary of f, which is the integral over c minus the integral over b minus the integral over a. And like I said earlier, the curl is 0. So this whole integral is 0. So this stuff here equals 0. Then I'll do the same thing with q. Likewise, the double integral over q of the curl of f is 0. But the boundary of q is b plus minus c plus. And so this also equals 0. So why do I subtract a from the boundary? Because if I think about the boundary orientation of D, you could think about sticking your thumb up in the Z direction and curling with your right fingers. And that curling motion would go like that. So the boundary orientation would be pushing A would be pushing that red curve in the opposite direction of A, if that makes sense. Alternatively, if you think about walking along A, if you walk in that direction, the region's to your right. And we always want the region to be our left, to be to our left. And so what do we do from here? Well, what do we care about? We care about the integral over c. C is c minus plus c plus. So I probably want to take this expression minus this expression. So I'm going to be supremely lazy. This minus this is 0 minus 0, so it's 0. But if I collect terms, what do I get? I have c minus negative c plus. That's c minus plus c plus, which is c. I've got negative the integral over a. And then I've got negative b minus b plus. That's minus b. And then we're told that the integral over a is negative 2. The integral over b is 4. So we get 4 minus 2, which is 2. Now do it. So that's a curve arithmetic type problem using Green's theorem instead of doing this whole like connect things with intermediary lines and stuff like that. You know, I was talking about this earlier, but I think this is a lot cleaner to me than if you think about what you'd have to do. You'd have to like go like duh and something like that or something. And, you know, you do it, but it would require a lot more naming. That's fun. Any questions about that one? So a private question I got was, so in general, when do we use Stokes versus Green's? So Green's, they're basically the same, but Green's theorem is for two-dimensional situations, and Stokes theorem is for three-dimensional situations. But other than that, they're pretty much the same. So if everything that you're doing is just in the plane, is in R2, then that would be a Green's theorem situation. And if everything you're doing is in 3 dimensions with like a surface or something, that would be Stokes theorem. Okay, so a private question I got was, could I explain what the story is with office hours during the final and the collaboration policy? I'm just confused on how Noah changed the final. So a couple things to say about that. Noah didn't really change. The only thing that Noah changed about the final is the whole top-up point system, like with the harder questions being bonus type questions. But the collaboration policy, like all that's the same. It's the same as it's been for previous exams, which is intentionally vague, but you know, I think he doesn't mind if you maybe talk with people about how to do something. The point is that at the end of the day, and like I said, this is intentionally vague because, you know, it's not like he, or it's not like we could say, don't collaborate, like don't talk to anyone. Like, we can't force that, right? But then if we say like, yeah, like collaborate, like, you know, just talk to everyone, then that would kind of be the other extreme that we want to avoid. So he's being intentionally vague there, and it's kind of up to you to just decide on your own how you feel about things. But whatever you do, at the end of the day, your solution should be in your own words. So even if you chatted with your friend or something about like, oh, try this or do this, the thing you want to avoid is like sending a picture of your solution to your friend and having your friend just copy things. As a grader, it's pretty easy to spot when that kind of thing happens. So whatever you do, everything should be in your own words. And then as far as office hours goes, you know, Noah's having office hours. I'm not planning on it right now. He might let me if I asked. I guess, I don't really know. But I don't really feel comfortable having office hours during a final exam because I don't want to have to walk that line of being too helpful. So we'll see, but don't expect it. So I would expect this to kind of be, this is it for me at least. And then, you know, I don't know. Yeah, so Noah posted his office hours on Campus Wire. So I don't know how helpful he'll be. The reason I'm nervous about that is because if you think about how office hours for some of these homework problem sets have gone, when there's, you know, like 100 people there or whatever, someone just says, hey, can we talk about number 3? And then what happens, I pretty much just do the whole problem, right? And I would not feel very comfortable about that. So what can you ask? Yeah, I don't know. Like, I mean, you can ask anything. I don't know how helpful he's going to be. Like maybe he'll be super helpful. Maybe if you're just like, I don't know how to do this, probably not. But ideally, I'd say if you have like specific, like if you're working on questions and you have specific questions that you're confused about, you could ask about that. But that's a great question. I don't really know, and that's why I don't quite feel comfortable holding office hours. Yeah, so I'm assuming, just like with all the other exams and stuff, I'm assuming you guys in James's class will have the exact same final. That's what I'm anticipating. Oh, and then I got a private question, tiny detail, but is surface independence explained by Stokes Theorem or the Divergence Theorem? Both. That's a great question. And that's kind of one of the points that I was making, is that, you know, Stokes Theorem is kind of this, or surface independence was originally explained by Stokes Theorem, but once you learn the Divergence Theorem, it also gives you surface independence, and it actually gives you even more. So it's the same thing as like path independence. On the one hand is explained by the fundamental theorem of conservative vector fields, but it's also explained by Green's theorem, and it's kind of subsumed by Green's theorem. Green's theorem gives you even more than path independence. So it's both. Wow. So if you guys actually want, I could sing one of the songs, but maybe let me say this first, and I'll I got another private question about the axes from another problem. I can come back to that. Let me kind of officially end here, and I'll just say that, first of all, it's been a great quarter. For some of you guys, I've said this already, but it's been a great year. I've known many of you since the summer or last fall or last winter. So hopefully I'll get to see you around sometime in the future somehow. But until then, good luck over the next few days. You'll be fine. Don't worry about it. It's just a grade. No matter what happens, you'll come out okay. So I don't know. It's been a good year of teaching, so I've enjoyed it. Hopefully you guys have too. And I appreciate you guys, I don't know, being so patient. And I think with this whole weird Zoom stuff, I don't know, it's been a weird experience. So that can be the end of the math part of the review session. I'll hang around for a little bit to answer some more questions, or if you really want to hear a shitty version of a song now that I'm losing my voice, I can do that too. Let me go back to, yeah, so this axis thing about that one problem. Sorry, the iPad froze. Let me bring that up again. You are all welcome. It's been my pleasure. Come on. Okay, there we go. So really quickly, quick private question was, does the fact that there's a potential function imply that the curl is 0, or is it the other way around? The first thing you said is correct. So if there's a potential function, then the curl is going to be 0. That's correct. If the curl is 0 and the domain is simply connected, then there will be a potential function. Okay, so then the other private question I got earlier was about this axes thing, which, yeah, that was kind of confusing. So let me re-say my answer here. For example, in this part, when I considered H makes sense for the y-axis. right? So I'm allowed to include the y-axis in the domain if I want to. So forget about all the other like exclusion things I was talking about. If I want to, I can include the y-axis. The only thing that I'm not allowed to include is the z-axis. And I really do actually want to include the y-axis because in order to define this green surface, that green surface goes through the y-axis, right? Like it includes the y-axis in part. So I really do need to define it. So I do need to include the y-axis. Likewise, in this other part, here we didn't have to remove the z-axis if we didn't want to, because the vector field in this part makes sense for the z-axis. And I did want to include the z-axis because it contains this region that I care about. So I don't know if that clears up any of the confusion there. And then, so another private question was, just to be sure, are gradients and potential functions the opposites of each other? Yeah. Yeah, you could think about it like that. Okay, cool. Okay, I really need to pee. I'll be back in a second. Sorry. Ooh, back at it. Okay, well, unless there are other questions, I can try singing a song. I'm actually curious though. I want to try something really quick. Can you hear me? Does this sound better at all? Okay, no response. How about now? Can you hear me? Does it sound better? Like, it's obviously a better microphone. I'm just curious if the sound quality comes through on Zoom or not. Okay, well, sorry for making you listen to my iPod headphones the entire quarter. I didn't know if this would actually sound a lot better on Zoom. Let me see if I can set something up. And yeah, I play guitar. That's about it. I can like play chords on a piano, but I play guitar a little bit. That's about it. Okay, so give me a sec. I need to figure something out. Nice. Yeah, I can give you the chords if you want sometime. I can put them in the description of the video. Let's see. Like, I want to be able to, or I want you to hear me. Can you still hear me talking, like from back here? Okay. Does it still sound okay? Can you hear the guitar as well? Okay, well, we can give this a shot. Let's see. All right. Also, I'm starting to lose my voice, if you can't tell already, so I apologize in advance if the voice doesn't sound too great. This will be an experiment. Okay, let's see. Here's a curve, it's long and lean. Vector field looks pretty neat. You're supposed to find the integral. Listen up, it's Joseph Green singing songs in quarantine. I'm here to help, so grab a new pencil. I know you're scared to take my hand. I'm with you through and through. Here's what we'll do. Take the curve, parameterize. Don't feel bad if it takes 3 tries. sure that you pick a T-domain. Before you go and compute our prime, pump the brakes and take some time. Check the orientation is the same. And now it's time to integrate. Check your work, don't make mistakes. And after that, just algebra remains. Well, here's a curve that circles you. It haunts your dreams and it haunts mine too. It's cornered you and it's calling out your name. Well, face your fears, don't be confused. You already know just what to do and make it through, 'cause everything's the same. I know you're scared, but take my hand, with you through and through. Here's what we'll do. Take the curve, parameterize. Don't feel bad if it takes 3 tries. Make sure that you pick a T-domain. Before you go and compute our prime, pump the brakes and take some time. Check the orientation is the same. Now it's time to integrate. Check your work, don't make mistakes. Don't freak out, it's just a grade. And after that, just algebra remains. All right, there you go. That's my goodbye for the year. Hopefully that sounded okay. I'm kind of curious to listen to the recording now. Nice. A raw acoustic version, I suppose. Yeah, if you guys if you want to make a cover, that would make my day. That'd be so funny. That'd be amazing. But well, I guess we can call it there. Unless there are more math questions, you know, I can still willing to answer math questions if you want. Yeah, I'll put the chords in the description of the video. So if you wanna practice it, I'll do that after this is over. I don't know about that, but thank you. That was my first live performance in a while. It's been a long, long time. I don't get to do that very often these days. So. I mean, not much. More so in high school. But then once I got to college, not so much. And then not really much at all in grad school. The math department has a talent show every year. Sometimes they don't have it. Like this year, there's no talent show, but they've had a they've had a talent show, so I've written a few songs for the math department talent show, and I've performed them there. But that's been about it. So other than that, I don't really get to do that very often. Okay, well, I'll stop recording at least.